Assalamualaikum and a very good day to Dr. Iskandar. Today, me and my team will present about our project. Our group is Group 4, which consists of me, Yasmin Zalika, Izin Hashi, Rutra Murthy, and Shatis Reddy. There are two parts in this presentation. We are Part A and Part B. For Part A, we will talk about calculation of relative permeability curve from capillary pressure data, and Part B is about the article discussion. So we pick Article 2 as our reference article, which is about laboratory measurement of relative permeability. Next, I'll pass the floor to Rutra for him to explain about Part A.
Hey everyone, my name is Rutra Murthy Visayendra, and today I want to walk through some of calculation which is capillary pressure measurement using centrifuge and done by group 4. Okay, so this is the part A, which is the part. Okay, so wait, let me choose the highlighter. Okay, uh, the sample we are using is sample number 21.2 and the depth is 3425.3. So the mile delta we are using is 0.26 mile delta. Okay, so the next is the approach we are using is binary approach. This is this is a formula for relative permeability of the wetting phase as and the absolute permeability just now I said 0.26 mile delta, and the tortuosity ratio is defined the equation which is the saturation minus connect water saturation and divided by 1 minus connect water saturation. And the tortuosity ratio of non-wetting phase from capillary pressure data we are using this formula is given here. Tortuosity ratio of non-wetting phase is defined by the equation which is 1 minus water saturation minus equilibrium saturation and divided by 1 minus connect water saturation non-wetting phase and minus by equilibrium saturation of non-wetting phase. Okay, let's go to the next. Okay, this is the graph. And over here we have a graph capillary pressure versus water saturation. We choose the graph because we have to measure the capillary pressure and inner core and mass water saturation calculated at inner core, and that's why we didn't choose mean saturation. Instead of we choose capillary pressure and saturation. And now we move to the calculation part. Plot the graph 1 over PC square versus saturation water, and we convert everything to the PC from bar to PSIA, and we use conversion factor 1 bar equals to 14.5 PSIA. We able to convert everything to oil fluid units, and which is easily applied to the 0.26 mile delta. So moving to the next slide, which is the calculation, and we converted the capillary pressure PSIA. So this is a pressure and we converted to PSIA. From that we calculate that 1 PCI square bracket PSIA negative 2, and we done the corresponding which is water saturation. Based on the graph, our CO2 oil saturation over here is 0 cause our graph starts from that direction. From there to here we can count as transition zone, and our irradiable water saturation is 3.428. So, and we plotted the graph 1 over PCI square by SWN. The line is over here is where I calculate the area on the graph trapezoid rule. This is the guys. So I integrate the graph 1 until 0, so is our absolute permeability is 0.26, and use the trapezoid rule, and this is the formula for wetting for the wetting phase, and that's how we are calculating our initial water saturation is 0.038 versus 0, as water saturation minus net water saturation equals to 0, and we proceed from 0.1 until 1, and the additional 1 is, okay, this is the additional 1, because our residual oil saturation 0 does. Our water saturation at the point must be 100%, and the value we obtain is 0, 0, then 0.0008, all the way until 0.00032115. Okay, so this is and we repeated the same process, but now for non-wetting phase or uh, relative oil permeability, we started from water saturation to 1 and then 0.9, 0.8, which is, let me show you. Okay, 1, then 0.9, 0.8, 0.7 until 0.0348, and the order is from down to up. After that, once we calculate the values and we integrate it format to this format and then we plotted the graph, which is initially look like this, and this is, we can see what is going on in here. Once we zoom out into the graph, and this is our graphs look like. Thank you guys.
Discussion part for relative permeability toward gas curve and oil, and also the time requirement per sample. For relative permeability toward gas curve, we can conclude that all methods which are Penn state method, single core dynamic, gas draft, and Hassler technique had produced the same result as we can see from the graph, which on figure 12 below and figure 13 at the top. For stationary liquid technique, the relative permeability toward gas curve produced is in strong agreement with other method for some cases. The relative permeability to gas produced by stationary liquid technique was lower than other method in the region of equilibrium gas saturation. In comparison to the value achieved by other technique, this led to an equilibrium gas saturation that was higher. Next, for relative permeability to oil, from the graph we can see that all methods which are single core dynamic, Penn state, and gas drive method all produce the same result. However, for gas drive method, the region with high oil saturation, it produces higher value of oil, while Hassler technique is the method that produces less oil than other three methods. Next, these are all the graphs that we use to compare all the methods and their outcome. The first picture is figure 9, second picture is figure 12, and last one is figure 13. Then, for time requirement, the Hassler technique took about roughly a week per sample to measure relative permeability, which caused a lot of time taken and making it the slowest way among all other techniques. For gas drive technique, it is the quickest method among all because it only took roughly about an hour only per sample to measure all the relative permeability curve. Next, for Penn state or single core technique, it can only measure 1 or 2 samples per day. And lastly, for stationary liquid technique, it can measure about 4 cores per day. Next, I'll pass the floor to Shatis to talk about how could the solution or result be extended or improved. Shatis, the floor is yours.
Hello. The questions ask that what are the practical implications of the solution and result. As you can see, the ratio of effective oil, gas or water permeability to absolute permeability is known as relative permeability to oil, gas or water, which defines as KRO, KRG or KRW. And the percentage varies from 0 to 1, which is used to represent a relative permeability. Relative permeability is also influenced by the type of pores and the wettability of formation. The next part is about when there's no obvious application, then how could be the relative permeability will be used in practice? Well, there's another technique which is called the polymer flooding process. Polymetric solution reduce the viscous fingering by lowering the mobility ratio and raising the viscosity of the displacing fluid. Thus, reduce effective permeability to water due to polymer absorption of rock surfaces increases the volumetric sweep efficiency and decreases the water out.
Hi, my name is Zain, and today I'll be talking about the problems faced in this paper. So the first things first is boundary effect. The discontinuity occurs where the fluid passes abruptly from the rock, a region of finite capillary pressure, into an open receiving vessel where this capillary pressure vanishes because of the capillary forces existing within the core. So the rock tends to retain the wetting phase at the outflow end. So this results in an accumulation of a wetting phase so that the saturation of that phase at the outflow boundary is maintained at a higher level than throughout the remainder of the core. So to tackle this problem, we use high rates of flow because it is shown by theoretical considerations based on Darcy's law that relative permeability, saturation relations, and capillary pressure saturation relations, that the saturation distribution along the core varies with different rates of flow. So it may be concluded that at the high rates of flow, the error introduced by the boundary effect may be so small that it will not be appreciably affect the measurements of relative permeability. Second off, we have the rate effect. So a problem faced is that there's no variation of relative permeability with variation of the rate in the absence of boundary effect that has been found. So deviations of relative permeability with the rate have been observed only where boundary effect are known to exist and disappear as the boundary effect vanishes. And thirdly, we have Hassler effect. In the problem, how to solve this problem is in the Hassler method, the pressure tabs should be placed on the side of the core so that each tab measures the true pressure over the cross-section of the core, unappreciably affected by any non-parallel flow. For example, the Penn State method could be modified so that a single core is used, obviating the need for reliance on capillary contact between sections. And next, we have limitations. And first limitation is since the relative permeability and saturations are not related linearly throughout the entire range of interest, the computed effective permeabilities are not unique with the calculated saturations. Secondly, there is not enough sufficient knowledge of the flow behavior of oil, water, and gas in porous materials to enable applicable analytical description of this to be made based on other measured rocks. And third, we have production characteristics of only certain processes are obtained from field data, and these are not available at the beginning of reservoir producing life, at which time they are desirable. Thank you.
The next part is about how could be the solution or result could be extended or improvised. First, increase the core saturation as the experiment conducted done with partially saturated core. Next, Hassler technique has the least value of relative permeability as other methods are very much recommended. Human error may occur during the core saturation, and usage of different core inaccurate results, as the author states that Penn State method needs longer core so that an optimum result could be obtained. The next question is about are the application other than those given by the author where solution or concepts in the solution could be applied. There's other technique called as unsteady technique, which involve a single experiment in which fluid introduced into a rock sample. The techniques are furthermore broken down into 4 subcategories, which are high rate categories, low techniques and centrifuge techniques, and stationary liquid techniques. Thank you.